Alright, everybody. Today we're going to talk a little bit about chemical kinetics. So, consider the following chemical reaction here, where we have NO gas reacting with H2 gas to form N2 and water. Now, we could write a generic rate law for this reaction in the following way, where the rate of the reaction is going to equal K, some rate law constant, times the concentration of our first reagent, NO, raised to some exponent, times the concentration of our other reagent, also raised to some exponent. Now, in order to figure out what the value of X is and what the value of Y is, we need to run some reactions here. So, here I have three reactions. Reaction 1, 2, and 3. And here I have the concentration of NO for all of those reactions. I have the concentration of H2 for those reactions. And I have the corresponding rate that would be measured for each of these reactions. And so, based off of these values here, we can actually come up with some rate law equations based off of these values and our generic rate law. So, if we were to write a rate law equation using this generic version of the equation, using reaction 1, we would have the rate of reaction 1 equal to K times the concentration of NO times the concentration of H2. Okay, and we're going to do the same thing for reaction 2 and the same thing for reaction 3 here. Now, just for fun, let's say we took a ratio of equations here. I'm going to take a ratio of this equation, this third equation, to this first equation here. So we'll have 4.92 times 10 to the minus third equal to K times the concentration of NO raised to some exponent times the concentration of H2 for that reaction raised to some exponent. And we're going to divide that by, remember, equation 1, which was 1.23 times 10 to the minus third. That was the rate for equation 1. And that's going to equal K times the concentration of NO for that reaction raised to some exponent times the concentration of H2 for that reaction raised to some exponent. Now, I took a ratio of equation 3 and equation 1 in order to find a value for X. You see, the only thing that really changed between these two reactions, that is the only thing that's going to cause a change in the rates here, would be the fact that we changed the concentration of NO. We kept the concentration of H2 here constant. So we changed one of our variables to see how that would change the rate as a whole. So if we take this 4.92 times 10 to the minus third and we divide that by 1.23 times 10 to the minus third, that should simplify to 4. Now over here, we have K in the numerator, we have K in the denominator, so I'm going to go ahead and cross that out. We have 0.10 to the y in the numerator, and we have 0.10 to the y in the denominator, so I'm going to go ahead and get rid of that as well. Now, 0.2 divided by 0.1 should simplify to 2. And since both of those terms have an x in them, this will actually simplify to 2 to the x. So, when we took a ratio of equation 3 and equation 1, we simplified that down to 4 equals 2 to the x. Now, what exponent could you raise the number 2 to get 4? Well, if we let x equal 2, then 2 to the second power will equal 4. What this tells us is that our reaction is second order with respect to NO. Now we're going to do something similar to figure out the concentration, the order of H2. So we have to compare two reactions where the concentration of NO is held constant, but the concentration of H2 changes. So coming back up here to this table, it looks like if we compare reaction 2 to reaction 1, we'll have a constant concentration of NO, but we'll have a changing concentration of H2. So, down here, this is exactly what I did. I took a ratio of the rate law, the generic rate law equations that we wrote up here for reaction 2 and reaction 1. That's exactly what I have here. On the numerator, we have reaction 2's generic rate law equation, and in the denominator, I have the generic rate law equation for reaction 1. So over here, if we have 2.46 times 10 to the minus third, and we divide that by 1.23 times 10 to the minus third, that should simplify down to 2 on this side of the equation. Now over here, we have k in the numerator and the denominator, so I'm going to go ahead and cross those out. We have 0.10 to the second power divided by 0.10 times 10 to the second power, right? This is the concentration of NO, and I put these 2's here because, well, we figured out that the order of NO was second order. But since these numbers are the same here in the numerator and the denominator, I'm going to cross those out. So this just leaves 0.20 to the y divided by 0.10 to the y on the right side of this equation here. So if we take 0.2 and divide by 0.1, that'll give us 2. And both of those were to the y, so we'll still have this y exponent here. Now if we take this 2 and we raise that to the first power, that'll give us this 2. What this tells us is that our overall reaction is first order with respect to H2 up here, right? So then we can write an overall rate law where the rate equals K, some rate constant, times the concentration of NO raised to the second power, times the concentration of H2 raised to the first power. And there you have it. That's how you figure out a rate law equation. Even if you don't know these orders, these exponents here, you can figure them out by running some reactions, keeping one variable constant but changing the other, and then seeing how the rate changes. So, hopefully that makes sense, guys. If you have any questions or comments, just let me know in the comments. And as always, take care.